There is a place in the universe that is colder than space itself, colder than the leftover glow of the Big Bang, colder than the gentle cosmic hum that fills every other corner of existence, colder, in fact, than almost anything that should be possible. It is not a black hole. It is not a dead star. It is a soft, glowing, ghostly cloud drifting in the deep south of the sky, in a constellation we cannot see from the northern hemisphere. Its name is the Boomerang Nebula. And the strangest thing about it is this: the cosmos on its own has a natural temperature. Even the emptiest, darkest parts of space are warmed very slightly by the cosmic microwave background, the faint afterglow of the Big Bang still drifting through the universe nearly 14 billion years after the beginning of everything. That background temperature is 2.7 Kelvin, about minus 270 degrees Celsius. The Boomerang Nebula is colder than that. It sits at roughly 1 Kelvin, minus 272 degrees Celsius, 1 degree above absolute zero, the coldest temperature physics allows. How does anything become colder than the universe it lives inside? That is the quiet mystery at the heart of this place. Welcome to Sleeping Galaxy. Tonight, we will drift slowly toward the Boomerang Nebula. We will visit the dying star at its center, a star that is, right now, releasing a slow exhalation of gas into space. We will learn how that exhalation, expanding outward over thousands of years, has cooled to a temperature lower than the cosmos itself. We will sit with the gentle paradox at the heart of this place, that the warmest things, in their endings, sometimes become the coldest things in all of creation. So close your eyes if you wish, or look up if you can. The night is long, the cosmos is patient, and tonight we travel to the coldest place in the universe. The first time anyone noticed the Boomerang Nebula, no one knew it was special. It was the late 1970s. A small group of astronomers in South Africa were surveying the southern sky, looking for objects that had not yet been catalogued. The sky in the southern hemisphere is rich, especially through the band of the Milky Way. There are many faint, lonely things drifting in those depths that have never been touched by light from a major telescope. In 1979, two astronomers, Gus Wegner and Ian Glass, were working through data from the European Southern Observatory's Quick Blue Survey. They noticed something faint in the constellation Centaurus, a small, soft, lopsided shape. They wrote it down as a butterfly-like nebula, a bow tie shape perhaps. A year later, in 1980, two other astronomers, Keith Taylor of the University of New South Wales and Mike Scarrett, looked at the same object through a different telescope, the Anglo-Australian Telescope at Siding Spring Observatory in Australia. They saw the asymmetry more clearly. To them, it looked like a boomerang, a curved, slightly lopsided shape against the deep dark of southern space. The name stuck, Boomerang Nebula, a small, quiet object far in the southern sky, about 5,000 light-years from Earth. For more than a decade, that was all anyone knew of it. It was simply another pre-planetary nebula, a small dying star in the slow process of becoming a planetary nebula. There are many such objects in the galaxy. The boomerang was not, at first, especially remarkable. It was faint, it was distant, it was strangely shaped. It was, in the great catalog of dying stars, simply one more entry. Then, in 1995, something unexpected happened. Two astronomers, Raghvendra Sahai of NASA's Jet Propulsion Laboratory and Lars-Åke Niemann of the Swedish ESO submillimeter telescope in Chile pointed a 15-meter radio telescope at the Boomerang. They were studying the gas drifting outward from the central star. They wanted to measure how fast the gas was moving, how dense it was, how warm. The answer to that last question stopped them. The gas was not warm. It was not even cool by cosmic standards. It was somehow colder than the cosmic background radiation itself. This is a strange thing to say. Let us approach it gently. The cosmic microwave background is the leftover light of the Big Bang, the moment nearly 14 billion years ago when the universe first became transparent to light. As the universe has expanded, that ancient light has cooled. It now sits at a temperature of about 2.7 Kelvin. Every direction we look in deep space, that gentle warmth is there. It fills the cosmos. It is the natural default background temperature of everything. Almost nothing in the universe is colder than the cosmic background. Things are usually warmer because they are warmed by stars, by light, by friction, by the slow thermal equilibrium of the cosmos. But the Boomerang Nebula was below it. Sahai and Niemann measured a temperature of approximately 1 Kelvin, just 1 degree above absolute zero, the absolute lowest temperature the laws of physics allow. The gas in the Boomerang was so cold that it was actually absorbing the cosmic microwave background rather than radiating against it. The background light was passing through, and the nebula was eating some of that gentle warmth. It appeared on their instruments as a faint shadow against the soft glow of the early universe. This was startling. It made the Boomerang Nebula the coldest known object in the entire universe, colder than anything else astronomers had ever measured, colder than the dust at the edge of distant galaxies, colder than the empty voids between stars, colder than the deep space between the spiral arms of the Milky Way. A small, dying nebula in a constellation we cannot easily see from the northern hemisphere, and within it, the coldest place anywhere in all of creation. There was, of course, an immediate question. How? How could anything in the cosmos be colder than the cosmos itself? The answer is gentle and elegant and almost domestic. It is the same answer that explains why your refrigerator gets cold. We will come to that slowly in the next chapter. But for now, simply rest with the image. A faint cloud in the deep south of the sky, a dying star at its heart, and around it the coldest gas anywhere in the universe, quietly absorbing the warmth of the Big Bang. There is a small experiment you can do almost anywhere. If you hold a can of compressed air, the kind people use to clean keyboards, and you press the trigger, releasing the gas inside, the can becomes cold, almost painfully cold, if you hold it long enough. Frost may form on the outside. You have not added anything cold to the can. You have not put it in a freezer. The cooling came from the simple act of release, of expansion. The gas inside, rushing outward into the air, became colder as it went. This is one of the gentlest secrets of thermodynamics. When a gas expands quickly, with no external heat source, it cools. Its energy is spread across a larger volume. Its molecules, which were close together and bumping into each other constantly, are now farther apart. They have less energy to share. They become quieter, slower, colder. This is called adiabatic expansion. It is the same principle that allows a refrigerator to work. The refrigerator compresses a gas, then lets it expand inside the coils at the back. The expansion absorbs heat from the inside of the refrigerator and releases it into your kitchen. It is a quiet, continuous, adiabatic process. The Boomerang Nebula is, in a sense, the universe's largest refrigerator. At its center sits a dying star, a star much like our sun but slightly heavier and now near the end of its life. For perhaps thousands of years, this star has been doing something extreme. It has been losing its outer layers, not slowly, but with great force. Streams of gas are being ejected from its surface at very high speeds, about 150 kilometers every second. This is far faster than the gentle stellar winds that come off ordinary stars like our sun. Our sun loses material too slowly into a quiet solar wind, but the sun's outflow is a soft breath. The boomerang's outflow is more like an exhalation that will not stop. In just the last 1,500 years, the central star of the Boomerang Nebula has lost roughly 1.5 times the mass of our entire sun. That is an enormous amount of material leaving the star at high speed, expanding outward into the surrounding cosmos. And here is where the cold begins. That ejected gas is moving outward into emptier and emptier space. As it expands, it has nothing to hold it in. There is no pressure outside the cloud pushing back against the gas. It can simply spread, and as it spreads, it cools. Adiabatic expansion on a cosmic scale. The math is gentle but firm. When a gas expands and no heat is added from outside, its temperature drops. The more it expands, the more it cools. The boomerang's outflow is expanding far faster and for far longer than any human refrigerator. The result is an extraordinarily cold region of gas that has been cooling steadily for over 1,000 years, with no external source of warmth. The natural background temperature of space, as we mentioned, is 2.7 Kelvin, the temperature of the cosmic microwave background. That radiation does try gently to warm everything in the universe. But for the Boomerang Nebula, the cooling from expansion is happening faster than the gentle heating from the background. The gas continues to drop in temperature, down past 2.7 Kelvin, down past 2, down past 1.5, down to about 1 Kelvin, 1 degree above absolute zero. It is, in this sense, a perfectly natural cold. There is no exotic physics involved. There are no mysterious forces. There is only a dying star exhaling gas faster than the universe can warm it. But the result is extraordinary. The boomerang has become, by this slow, patient cooling, the coldest place known in nature. Colder than the surface of Pluto, which sits at about 40 Kelvin. Colder than the rings of Saturn. Colder than the deep voids between stars. Colder than anything humans have observed without using laboratory equipment. There are colder places, in a sense. In laboratories on Earth, scientists have used precisely controlled experiments to create ultra-cold atomic gases, temperatures down to billionths of a Kelvin. On the International Space Station, an instrument called the Cold Atom Lab has achieved temperatures so low that they almost defy description. But these are tiny, careful, human-built bubbles of cold. They exist for fractions of a second in small chambers. They are not natural. The boomerang is natural. It is a vast, light-year-wide cloud of gas drifting through deep space at less than 1 degree above absolute zero. And it has been doing so for thousands of years. It is the universe cooling itself, quietly, patiently, with nothing more than physics and time, and a single dying star releasing its breath into the cold and patient dark. If you could approach the Boomerang Nebula slowly, drifting toward it through deep space, you would see something strange. From a distance, in visible light, it looks like a soft, glowing bow tie, or a butterfly with two delicate wings extending in opposite directions from a small, bright center. This is how the Hubble Space Telescope first showed it, in the early 2000s. A symmetric shape, faintly luminous, drifting against the southern sky. But that visible light is not the nebula itself. It is reflected starlight. The cold gas at the heart of the boomerang does not glow. It is far too cold to emit visible light. What we see when we look at the nebula in the visible spectrum is light from the dying central star. Light that has bounced off the dust and gas surrounding it, scattering outward in two opposing cones. The true shape of the boomerang is something different, and it took a much more powerful telescope to see it. In the early 2010s, astronomers turned a remarkable instrument toward the nebula, the Atacama Large Millimeter Array, known by the gentler name ALMA. It sits high in the Chilean Andes on a dry plateau more than 5,000 meters above sea level. It is not one telescope, but many. 66 precision antennas working together as a single enormous eye, looking at the universe in millimeter wavelengths, the kind of long, gentle, infrared warm light that cold gas does emit. When ALMA looked at the boomerang, it saw something Hubble could not. The true structure of the nebula is not really a bow tie. It is an hourglass, a delicate, symmetrical, hollow shape, two opposing bubbles of gas, narrow at the middle, expanding outward at the top and bottom. Around this hourglass, ALMA saw something else, a great, roughly spherical envelope of cold gas, much larger than the hourglass itself, a cocoon of slow molecules surrounding the inner structure on every side. The hourglass is fast. The outer envelope is slow. The hourglass is bright. The outer envelope is dim. The hourglass is where the dying star is currently focused. The outer envelope is the older material, gas that left the star earlier in its eruption and has had more time to expand and to cool. The coldest part of the boomerang sits in that outer envelope, the gas that has been moving outward the longest, the gas that has cooled the most. At the very center of all this, the source of the entire structure, is the dying star. It is a star much like our sun once was, perhaps a little heavier. Now, after billions of years of patient hydrogen burning, it is in the final stages of its life. The hydrogen at its core has long since been consumed. Helium fusion has come and gone. The star is now in a phase astronomers call the post-asymptotic giant branch, a brief moment in the lives of medium-sized stars when the outer layers are being violently shed and the inner core is slowly being exposed. This phase does not last long, perhaps 1,000 years, perhaps a few thousand. By the standards of stellar lives, which span billions of years, it is a soft, brief moment. In just the last 1,500 years, the star has lost an extraordinary amount of mass, roughly 1.5 times the entire mass of our sun. Imagine that. A star in only the last 15 centuries has shed material equivalent to 1.5 complete suns into the surrounding space. This is what creates the great hourglass structure. This is what creates the cold, expanding envelope. We do not know precisely why the loss has been so violent. Most preplanetary nebulae lose mass, but not at this rate. and not in this way. There is some indication that the central star may once have had a companion, a smaller star perhaps, that was drawn in too close and spiraled into the larger star's outer layers sometime in the past. The energy of that slow collision may have helped drive the great outflow we see now. This is speculation. We may never know for certain. The companion star, if it ever existed, is no longer there. It has been consumed, or thrown clear, or hidden inside the bright central source we now see only as a single point of light. What we do know is the current picture: a small, hot, dying star at the center, an hourglass of fast, bright gas just around it, a vast, cold, slow envelope surrounding everything, and throughout it all, the gentle, ongoing process of adiabatic cooling, the cosmos quietly turning warmth into expansion, expansion into cold, a nebula at the very edge of absolute zero, a star losing itself very slowly into the surrounding dark, a shape that we cannot quite name, a boomerang, a bow tie, an hourglass, a ghost. The Boomerang Nebula is, in its quiet way, one of the most beautiful objects in the southern sky. And if you could ever stand inside it, surrounded by gas 1 degree above absolute zero, you would feel almost nothing. The molecules around you would be moving so slowly, so gently, that there would be no warmth at all, no friction, no motion you could sense. A perfect, gentle, ultra-cold silence, far from anywhere, below even the temperature of space itself. It is worth pausing here to ask a quiet question. How cold is 1 Kelvin, really? What does it compare to in the rest of the cosmos? Is the boomerang truly the coldest? Or are there other quiet, frigid places we should sit with for a moment? Let us drift gently through the cosmic cold. Begin close to home. Begin with winter. The coldest temperature ever recorded on Earth's surface is about -89 degrees Celsius. This was measured at a Soviet research station in Antarctica in 1983. Even the harshest places on our planet, the polar plateaus, the deep glacial interiors, never drop below about -90. In Kelvin, that is roughly 184. Cold by human standards. Cold enough that exposed skin freezes in seconds. Cold enough that breath crystallizes in the air. But not in the cosmic sense. Cold. Move outward. The surface of the moon, on its dark side, where the sun has not touched in days, drops to about -180 degrees Celsius, roughly 93 Kelvin. The moon, with no atmosphere, no insulation, has nothing to hold heat in. The shadow side becomes truly frigid, and yet still warmer than our destination tonight by nearly 100 times. Continue outward. Mars, at its winter poles, reaches about -143 degrees Celsius, around 130 Kelvin. Carbon dioxide freezes out of the thin Martian atmosphere and falls as a delicate frost, a kind of dry ice snow, still warm by boomerang standards. Pluto, a small frozen world in the outer solar system, its surface temperature averages around 44 Kelvin, cold enough that nitrogen freezes solid, forming great plains of pale ice. Cold enough that the very atmosphere, in the planet's longer winter, occasionally collapses onto the surface as snow, and yet still over 40 times warmer than the heart of the boomerang. Move past the planets, past the Kuiper belt, past the Oort cloud, into the interstellar gap between solar systems, where there is almost nothing, no sunlight, no significant matter, only the gentle bath of the cosmic microwave background. The background temperature of empty space is 2.7 Kelvin, the leftover warmth of the Big Bang, still drifting through everywhere. This is, in most places, the lowest temperature the cosmos provides naturally. Even the deepest, darkest voids between galaxies sit at roughly this temperature. The Boomerang Nebula sits below this, at 1 Kelvin, about half the temperature of the background, about 1/3 of a degree above absolute zero, the lowest temperature physics allows. There are very few other places known to be colder. In 1995, the same year the boomerang's true coldness was first measured, physicists on Earth achieved something similar in a small laboratory. Using a technique called laser cooling, they slowed atoms of rubidium gas almost to a complete stop. They reached temperatures of less than 1/1000th of a Kelvin. They produced what is called a Bose-Einstein condensate, a state of matter where the gas behaves in some sense as a single quantum object. This was extraordinarily cold, colder than the boomerang, but it was tiny, a small cloud of atoms in a single experiment, in a single chamber, lasting only fractions of a second. And in 2018, an experiment was installed on the International Space Station, the Cold Atom Lab. It produces ultra-cold quantum gases in the microgravity of orbit, where they can be held more stable than on Earth. Researchers have reached temperatures of picokelvins, trillionths of a Kelvin, for fleeting moments. These laboratory temperatures are, technically, colder than the boomerang. But they are not the cosmos. They are not nature. They are small, fragile, deliberately constructed places. The cold of the boomerang is something different, a vast, light-year-wide region of natural gas, drifting freely in space at less than 1 degree above absolute zero. The cold of the cosmos itself, achieved by nothing more than time and physics. There is something to think about in this distinction. Humans, in our laboratories, can briefly create temperatures lower than the boomerang, but only briefly, only in small, careful, deliberate corners. Nature, in the form of the Boomerang Nebula, holds its cold for thousands of years, across an enormous volume, with no help from any instrument. It is the cosmos's quiet, patient answer to the question, how cold can natural physics go? For now, the answer is the boomerang, 1 Kelvin, a small ghost shape in the southern sky, drifting at the very edge of what is allowed. And there may be others hidden out there that we have not yet found. Other dying stars in other distant corners, producing other ultra-cold outflows, other quiet bubbles of post-Big Bang cold, waiting patiently for telescopes that can see them. We may in time find something colder, but for now, the boomerang remains the gentle, lonely champion of cosmic cold, the coldest natural place we know, a small, dying nebula, 5,000 light-years away, in a southern constellation most of us cannot see, quietly outpacing the universe itself. The Boomerang Nebula will not remain the coldest place in the universe forever. It is, like everything, in motion. The dying star at its center is approaching the end of one phase of its life and the beginning of another. And as that change happens, the cold of the boomerang will end. This is one of the quiet truths of cosmic cold. It cannot be sustained forever. The same physics that produced the cold, adiabatic expansion of a violent stellar outflow, depends on the star continuing to lose mass at its current dramatic rate. And that rate will, eventually, slow. The outflow will weaken. The expansion will lessen. and the cosmic background gently warming everything will catch up. How long do we have? In cosmic terms, almost nothing. A few thousand years, perhaps less. The pre-planetary nebula phase, which the Boomerang is in right now, is one of the shortest stages in a star's life. Most stages last millions or billions of years. Hydrogen burning, the longest, can last over 10 billion years for a sun-like star. Helium burning, perhaps 100 million. The red giant phase, tens of thousands. But the pre-planetary nebula phase, the brief moment when a star has finished its main fusion phases, is rapidly shedding its outer layers and has not yet exposed its hot inner core, lasts only about 1,000 years, maybe a few thousand in the longer cases. The Boomerang, current estimates suggest, has been in this phase for roughly 1,500 years already. The star began its dramatic mass loss around the time the Roman Empire was falling. As the first medieval kingdoms rose in Europe, the Boomerang's gas was already racing outward, beginning its long cooling. In another 500, perhaps 1,000 years, this brief moment will end. What happens next is, in its own way, the opposite of cold. The dying star at the center of the Boomerang is currently hidden, wrapped in the very gas it is shedding. We see only a small, bright source through that gas. But as the mass loss continues, more and more of the star's outer envelope is being stripped away. Beneath that envelope sits the star's hot inner core, what will become a white dwarf. A white dwarf is a very small, very dense object, about the size of Earth, but containing roughly the mass of our Sun. Its surface temperature, when first exposed, can be 100,000 Kelvin or more. Hotter than almost anything else in the galaxy. Hot enough to emit intense ultraviolet light. When the central core of the Boomerang star becomes fully exposed, sometime in the next few thousand years, that ultraviolet light will pour outward into the surrounding gas. The gas, which is currently cold and quiet, will be illuminated. It will be heated. Slowly at first, then more quickly, the cold envelope will be warmed by the new, exposed, blazing core. The Boomerang will stop being the coldest place in the universe. It will become, instead, a true planetary nebula, a glowing, ionized, brightly colored shell of gas, like many other planetary nebulae we already see in the night sky. The Ring Nebula, the Helix Nebula, the Cat's Eye. These are all the late stages of similar dying stars, where the gas has been illuminated by the exposed white dwarf at the center, and now glows in shades of green and pink and gold. The Boomerang, in its time, will become one of them, a bright, beautiful fluorescent shape, glowing in many colors, vibrant, warm, no longer the coldest place we know. This is, in its own way, sad. There is something about cold places, quiet places, that the heart returns to. The Boomerang, as it is now, is silent, frozen, almost reverent. To imagine it glowing, ionized, full of bright color, beautiful as it will be, feels like the loss of something patient and rare. But the cosmos does not preserve. It transforms. Every cold thing eventually warms. Every quiet thing eventually becomes loud. Stars, in their endings, do not stay at one temperature. They cycle. They breathe. They become, in turn, every form their physics allows. And so, in a few thousand years, the coldest place in the universe will become something else. Some other dying nebula, somewhere else in the galaxy, may take its place. Or perhaps no nebula will. Perhaps the cold record will be empty for a while, waiting for the next. We do not know. Astronomers are still searching for other ultra-cold outflows. There may be similar objects hidden behind dust in other corners of the Milky Way and beyond. The boomerang may simply be the brightest example of something that quietly happens in many places. Every time a medium-sized star ends with sufficient violence in this very particular way. It is also worth thinking about this. The cold of the boomerang is not a sad thing. It is not a defeat of warmth. It is the gentle byproduct of a star-making space for new things. The mass being ejected from that dying star will, in time, drift outward into the galaxy. It will mix with other clouds of gas. It will cool, then warm again, then collapse, then form new stars, new planets, new possibilities. The Boomerang Nebula is, in this sense, the cold breath of the cosmos before something new begins. And in another 20 or 30,000 years, when astronomers look at this region of space, if anyone is looking, they may see a small glowing planetary nebula in the southern constellation Centaurus. They may notice that it was once, briefly, the coldest place in the universe. They will not be able to recover that cold. It will be gone, like all things. But for now, tonight, the boomerang still burns with its strange, gentle, ultra-cold fire, below the temperature of space itself. 1 Kelvin, a ghost shape in the southern sky, the coldest place we know, for just a little while longer. The night is quiet now. Somewhere far below the southern horizon, in a constellation most of us cannot see, the coldest place in the universe is gently expanding. A small dying star exhaling its last great breath into the surrounding dark. Around it, an envelope of gas at 1 degree above absolute zero, the very edge of what physics allows. There is no sound there, no motion that we could feel, no warmth at all, just stillness. We have visited many places in our journeys together. We have stood beside vast stars wider than solar systems. We have drifted to the largest black hole in the universe. We have followed rogue planets through the eternal cosmic night. And tonight, we sat with the coldest place anyone has ever found. There is something in all of these places that perhaps we recognize, a quietness, a slowness, a patience that we, in our short and busy lives, do not often touch. The cosmos is largely quiet. The cosmos is largely cold. The cosmos is largely empty. And these things, for some reason, do not feel like absences. They feel like the deep, slow, gentle state that everything settles into in the end. The Boomerang Nebula has been cooling quietly for 1,500 years. It will continue, perhaps another 1,000. Then it will warm again. Then it will fade. Then, in the long, slow turning of the galaxy, its gas will drift outward, mingle with other clouds, cool again, gather, and eventually, perhaps, form a new star, a new planet. Perhaps, somewhere in some unimaginable future, a new place for someone to sleep beneath. There is no need to remember any of this. The cosmos does not require us to remember. It simply, patiently continues. If you are still awake, that is all right. The night is long. If you are drifting toward sleep, even better. In a small ghost shape in the southern sky, gas drifts at 1 degree above absolute zero. The cosmos keeps watch. The cold is gentle. Everything is quiet. Sleep well, and good night.